Gana. Pero no es nada.
I mean, I think, yeah, you can hide. Oh, there we go.
Okay, welcome back. And now we'll continue with hadronic physics via lattice QCD. And so, Raul, glad to have you. Thank you.
Okay. Good afternoon, everybody. My name is Raul Briceno. I'm coming from Berkeley. How's everybody doing? Everybody's good, well fed, hopefully not too sleepy after lunch. So I've been given the impossible task of reviewing all of lattice QCD in 2 hours, which, just to give you a sense of how impossible that is, there's a little screenshot from last year's lattice conference, and this is just one day. So this is to say there's just many subfields within lattice QCD. It is a really growing field. Good fraction of folks being hired at faculty levels in the US are doing lattice QCD. It's really impossible for me to give you a broad sense of what the field looks like. And so what I figured I would give you is a little introduction into it. And for some reason, this clicker is not working. Let's see.
Oh, sorry, click.
Then I gotta click the page, right? There we go.
Thank you.
So instead of giving you like a broad strokes, introduction to the field, I'll give you a little bit of introduction into lattice QCD, and then I'll give you a bias sample in research in terms of the kind of research that I do within lattice QCD, which basically is outlined here. So my bread and butter is really QCD spectroscopy, which is relevant for many experiments out there, and I'll give you a little bit of a taste of why it's relevant today. But then, I'll do a little bit of hadron structure, nuclear structure, a little bit of fundamental symmetries, and I'd be happy to talk about this. Once you start going to finite temperature, finite density stuff, I have like a little bit of textbook knowledge, but not that much. So, I'd be happy to discuss these things, but I'm not an expert, okay? And so let me first try to give you a sense of why hadron spectroscopy is hard, why there's many puzzles, why you should continue to study it, and then we'll dive into lattice QCD itself. We can categorize states in QCD in many different ways. A simple way to start categorizing states into those that are absolutely stable. Here's a proton, our nuclei, us, but that's about it. There's not many things that are stable on their own. Then there's states that are electroweak stable. The opposite, electroweak unstable, but QCD stable. That is to say, if we turn off the electroweak sector of the standard model, these would be stable states, but otherwise these decay. And this is relevant because lattice QCD calculation, the vast majority of these today, the electroweak sector, we exactly turn it off. And so if we were to turn off that sector and study QCD on its own, the neutron, the pions, these are stable, and there's, a handful of these states that would still remain stable, something in the order of a dozen. Then there is the rest of the states, which are, the vast majority of the states that you see in the PDG, which are not just unstable due to the electroweak sector, but also unstable due to QCD. And these guys decay in timescales that are much smaller, many orders of magnitude more rapidly than the electroweak unstable states. And this is because they decay via the strong interaction, which is much stronger. And these decay to multi-particle states, 2 particles, 3 particles, and so forth. And these are, like I already emphasized, the vast majority of states. In fact, the first excited state of the nucleon, which is it goes by the name of the Roper, decays to 2 particles, but it also decays to 3 particles, roughly 50, somewhere between 25% to 50% at a time. And so if we want to understand the spectrum of QCD, which is the simplest thing that you would want to extract of any one theory, right? And we all want to understand QCD, you necessarily have to understand this third column of QCD, and these are much harder states to resolve, in part because they decay, in time scales that are much shorter than, these guys are never going to hit your detector. So we need to learn how to reconstruct these. And also we need to understand how to accommodate the fact that these appear in strongly coupled systems with many, multi-particle final states. And so this is needless to say, a challenge. Why is this interesting? Well, hopefully I already convinced you why it's interesting, but there's in fact we're right now in a resonance of spectroscopy that is really exciting with many puzzles out there. The LECB alone has discovered something in the order of 60 or more new candidates. Each one of these dots represents a candidate of a new particle that has been identified as a function of time, and none of these states have yet to be confirmed. None of these states we know for sure to be a state. We haven't been able to study these directly from QCD or the standard model. So if you want to resolve any puzzles, here's many puzzles. Okay, I'm going to zoom in into three particles that I think are particularly interesting. I'm not going to go through all these 60 states because I don't actually know all of them. But I'll give you three states that are particularly interesting, and each one of them tell a very completely different story that I think is fascinating about QCD. So one of them is called the X2370. The X refers to the fact that we up to recently didn't know that much about its properties. The number corresponds to its mass. It appears here in this. I really don't love this clicker. I'll stop using this clicker and use my hands. It was observed in an experiment BEST3, which is taking place in China, and it's seen as this broad peak right here in this energy distribution of a three-particle final state, where you have three particles. These are the three particles. Okay, and it's what they were able to recently observe is not just its mass, but also its angular momentum and parity and charge conjugation. And the experimentalists, what they observe is that this mass and parity roughly coincides with glue ball candidates in quench calculations in lattice QCD, and so they hypothesize that this is potentially a glue ball state, and we can talk about that later. So if we want to search for glue balls, which at this point we don't actually have any smoking gun of a definite glue ball, this could be a potential candidate. So there's a puzzle: is it indeed a glue ball or not? Other interesting states include the TCC. This is a state that was seen in LECB a few years ago, and is seen again in a three-particle decay. This time you have a D star final state, but the D star itself is a resonance, which then decays to a D and another pion. A D is made of a charm quark and a light antiquark, and so you have three final states. These, of course, then decay electroweakly, and you reconstruct the final state. Which is much more complicated, but then you can still look at the energy distribution of these guys. And as a function of the energy of this three-particle system, you have this nice little bump, and this nice bump corresponds to this potential state. And the point is that this guy, the minimal flavor content that you can have is two charms and two light antiquarks, which corresponds to it potentially being a tetraquark. And so that's quite exciting. In fact, this is a most likely candidate for a tetraquark out there. Then there are pentaquarks. These are states that have 5 quarks, and so 3 quarks and 2 antiquarks. And these have been seen in LHCb again as an energy distribution, in this case, of 2 particles, the J psi and the proton. It is still seen in a 3-particle decay, but you have in this case, you have a kaon that is basically, you can think of it as a spectator, and then the pentaquark are observed, and then these decay to J psi and proton. And these are seen as nice little peaks in this energy distribution of the J psi and the proton. Here's one of them, here's another one, here's another one. And you can see this peaks in the energy distribution. The reason why these states are, hard to say definitively that they exist, even though we see these nice little peaks experimentally, is because they take place in these rather complicated reactions. If they're actual states of QCD, then they would be universal. Regardless of the mechanism that we would be observing them, they should appear. And so there's been searches for these guys here in the US. So there's an experiment that takes place in Europe. Here's an experiment that takes place in the US. It's a much simpler experiment where you have a target proton. This is the GlueX experiment at Jefferson Lab. So you have a target proton being hit with a photon. In principle, it should create a pentaquark with the same energies that are seen in the other decays in LHCb. And they scan the energy region of the J psi proton, and what you see is that there's this kind of bumpy-like behavior in the cross section, but there's no smoking gun for a pentaquark. There's no nice peak distribution. And so it could be that pentaquarks like to live in Europe and not in the US. Or it could be that those states that are seen in HCB are not really states. They're actually just kinematic singularities that have nothing to do with actual states. And so this brings me to, the kinds of questions that us as theorists are trying to answer, both in spectroscopy, but more generally. First, we want to try to understand, what are the actual states in QCD, right? Which ones of these bumps that are seen in cross sections are actual states of QCD as opposed to kinematic singularities? There's many kinematic singularities that can appear. These are infrared singularities. I'm not talking about ultraviolet. Honest to God, infrared singularities, you can have logarithmic or even more complicated singularities that can appear that can lead to these kind of, bumpy-like structures, right? If I wash out a logarithm that kind of looks like a bump, meanwhile, an honest to God state would be a pole in a scattering amplitude. And this comes from LSC in quantum field theory, which is something I would be happy to talk about in further detail. So, something like this, a behavior like this, where S is the Mandelstam variable, where S is equal to the center mass energy squared. If you have a pole in that amplitude, or with a real part corresponding to the mass, the imaginary part corresponding to the width, up to a factor of 2, that would be an actual honest to God state. Meanwhile, something like this is just a poser. Okay. So the first question we want to answer is, what are the actual states of the theory? Second, once we determine a given state, can we start to slice it and dice it and learn about its structure, right? We've been doing this quite well for simple things like the proton, even for light nuclei, but can we get a general structure of the low-lying states of QCD? And then finally, can we get some structural information so that we can then resolve these states and say, aha, one, by looking at, the radius or the partonic distribution of these states, can we say that, there's potentially one state out there that is definitively a glue ball or more likely to be a glue ball, or it might have some, molecular like structure or tetraquark or pentaquark, et cetera, And then generally, more broadly, can we deduce something about the general principles of QCD by looking at the patterns in the spectrum and the internal structure of these states? Ultimately, that's what we want to do, right? The reason why we're so fascinated with the proton and other light nuclei in terms of trying to understand the structure is because we really want to understand how quarks, what are the general principles as to how quarks come together to form us, right? And so we want to get that, but more generally from the whole spectrum. And so if we want to tackle these class of problems and many more, we need to have a tool that is non-perturbative, because QCD itself is non-perturbative, that doesn't compromise the dynamics of the theory. It can allow us to have not just constructing single particle states, but as well as multi-particle states. And the only naming in town at this point is lattice QCD. And so that's very very broadly my introduction as to why you should care about lattice QCD. There's many motivations, but this is the thing that drew me into the field. And so I figured maybe this is a good time for me to stop for questions, comments, concerns before I go on. I know that I can talk a little fast. Yeah, what's up? Question. I'll talk about it. So my goal is by tomorrow to talk about scattering processes. And then from there, I'll be able to tell you how we are able to get resonance information from lattice calculations. I will talk about that by tomorrow. I'll tell you about how far we can go today. I'll tell you about what I think of the limitations, which are unclear. But I can tell you what we can do today, what I hope we can do in the next 5 years, and what I think are the broad limitations. If I don't answer this correctly by tomorrow, ask me again. Anything else? Okay, so here's my broad outline. So today, maybe tomorrow, I'll talk about basically the basics of lattice QCD. And then I'll talk a little bit about cutting edge and research, which I'll largely focus on my own research because that's what I can best talk about. So first question, does lattice QCD works? It does. Basically, that's the short answer. I can give you many examples of this, how it works today. But I think these are two beautiful examples, and none of them involve me. I haven't published anything in this page, and so that tells you how unbiased I am. That's of course a joke, but this is a calculation by the BMW collaboration, not the car maker, where they've been able to determine the mass splitting of light particles, not just using QCD, but also incorporating the electromagnetic, also including QED. So they've been able to calculate the mass splitting of the neutron and the proton, as well as isospin partners for an array of different particles, and they compare rather well with the experiment. This is a remarkably impressive calculation. Physical point, multiple lattice spacings, yada, yada, yada. Quite beautiful, and it agrees with the experiment. Here's another example of a calculation that has been studied by many folks around the world by different collaborations. And what they've been able to determine is the axial coupling of the nucleon. So if you look at neutron decay, the neutron itself is unstable. You leave it alone for like 15 minutes, it will decay to a proton, antineutrino, and an electron. And this reaction is determined purely by kinematics, and then one coupling, which is the axial coupling, at least at the zero virtuality point. And these different calculations using very different actions, different systematics, different resources, different statistics, et cetera, get broadly very consistent results. There's fluctuations, but if you zoom out, everything largely agrees. These calculations have been done with dynamically up and down quark masses, up and down in strange, up and down in strange and charm, and everything broadly agrees. This is what is called, this is an average of the community. There's the flavor lattice averaging group, which every so many years comes out with an average. There's different quantities, and they put different weights associated with the level of systematics. So reds, they've taken into account less systematics, and green, solid green is better than not solid green, et cetera, et cetera. Nevertheless, things agree roughly pretty well. So this is all to say, as far as we can see, places where people have done lattice calculations systematically, taking continual limits, et cetera, there's no real tension with experiment. And that's really amazing. I can't find one example where there's real significant tension with experiment. And so, okay, that's my first check mark. But the real question that I want to talk about today is, why does it work? Why should we trust this tool? And from here, I'm going to assume that you haven't seen lattice to any extent. And so let's go to the basics, okay? I think when people first encounter the idea of lattice, you just like plug it into your computer, you put in your numbers, and voila, something comes out, right? Of course, it's not that simple. And to really understand the basics, we need to go back to the QCD Lagrangian. So QCD, quite beautiful. It's described by just one coupling, right? Which, in order for the theory to be self-consistent, that coupling has to be energy dependent. And at large energies, this thing has to be small, or it is small. At small energies is large, non-perturbative, and many questions that we're interested in lie in this region, right? Confinement, origin of mass, the formation of matter, et cetera, et cetera. If you're able to solve the theory non-perturbatively, analytically, you will certainly be a strong candidate for a Nobel Prize. So don't lose hope. Nevertheless, that's a higher toll than I'm able to, shoot for. Instead, we can resort to numerical tools, namely lattice QCD, which don't make approximations about the dynamics. And so instead, what we're going to do is discretize the theory, use a path integral representation, and do statistical methods to evaluate the theory. That's a lot of mumbo jumbo. Let's dive into each one of those details. So first, if you haven't thought about the path integral in a while, the path integral representation in a while, I don't know. I actually don't know. I mean, it's just something that people haven't thought about in a while. Maybe I shouldn't do it. I won't ask. I'll just do it, and then I'll go fast in some parts and slower in others. So if you haven't thought about the path integral in a while, representation in a while, let's just think about quantum mechanics. You have some state at some original point in time, some original point in space-time, some later time. We can grab the time evolution operator, break it up into infinitesimal amounts, and then after a little bit of massaging, we can write this expectation value of the time evolution operator as an integral over all possible paths weighted by the action, okay? And this is the classical action. And the classical action minimizes the path between, the classical path is a minimum of the action between these 2 points. But of course, quantum mechanics is a little more agnostic, it doesn't want to go just one path, it wants to go over all paths. weighted by this exponential, okay? And this is the way that we derive this, right? In quantum mechanics is typically we grab time and we discretize it, right? We introduce a set of points that we, in corresponding to each time that we integrate. And then eventually we take the continuum limit, right? And that's how we derive it, right? Lattice QCD basically amounts to saying, let's do that, but don't take the continuum limit. Let's do that continuum limit after the fact. And let's do that also for space, okay? And so that allows us to construct a mesh in which we can numerically evaluate these kinds of integrals, right? And so that's conceptually the starting point. But that's for quantum mechanics. So in classical mechanics, what you have in the path integral are not integral over physical paths, but rather different field configurations. So if we consider a classical field, right, we can have various different field configurations that represent a given field. And in general, these guys are not bounded. But we can do the same thing. We can grab the fields, discretize space. And so for some given point in space, for some reason, I have nice little points associated with them, but for some reason, the PDF does not resolve this. Hopefully, this is not a general problem. So yeah, what's up?
It works on the PDF on the website. So anyone looking on the computer.
Awesome. Okay. All right. So it's not a problem there, but it's a problem here.
Yeah.
Sounds good. Use your imagination. There's some points here. Basically, what we can do is discretize space and then sample the fields along those points in space. We choose some discrete points in space, and there are oh no, but the equations are not going to work. There's an equation missing. Okay, well,
You want to try a switch or?
I'm debating how emotionally devastated I would be. Yeah, maybe. Is it too much of a hassle?
Try 2 minutes and see if.
Okay.
We have USB-C.
Oh, you mean like attaching it to my computer?
Yeah.
Oh, yeah, sure. Meanwhile, does anybody have any questions? I mean, we have two options. You either ask questions or I start pointing my finger at people and make them ask questions. Oh, because it's the Zooms, huh? It's okay. It's okay. Is your computer's not a Mac, right?
No.
That's the problem. Okay. Yeah. For some reason, like when the PDF comes out, and yours is a Mac. Oh no, yours is not a Mac.
I think you should be able to go on the website and open up the PDF and use that to present.
I think this is what it is.
Yeah, I downloaded it.
Oh,
Yeah, I downloaded the PDF.
Okay. Okay. It's okay. Let's just move on. I mean, at the end, I'm trying to motivate you guys into understanding this stuff. I don't want to go through every equation. Let's just use our hands and be hand wavy, and then I can go up to the board and go into further detail. But the idea is right. It's simple, right? It's just conceptually, we grab different points in space, and you can just imagine discrete, picking some discrete points, and within those points, that's where we'll sample our fields. Okay, and so that gives us a finite mesh of points. So we discretize space-time here, and so our measure where we integrate over our fields are just defined for those discrete points. In fact, that is the only way that we can actually rigorously define a measure in quantum field theories, right? If you've seen a QFT course, that's how you define it, and then you say, well, let's imagine some continuum limit. Here, let's not imagine the continuum limit. We can just do that calculation in that discretized space. And so, okay, so let me go up to the board. There's now key equations that are missing. So this this is my fault for using equations in a talk. I shouldn't have done that. So the issue that I was trying to address here is that if you have the path integral representation, even for a discrete set of points in space. Oh, this works.
Yeah, I'm stealing the screen, so I'm running off.
Oh, okay, fantastic.
So, yeah, so just double click, go to full screen there and I can,
If I double click this,
yeah, just.
Green one,
Or,
the green button.
the green button.
No, the upper left.
on the left.
Upper left.
The upper left.
Of the window.
Yeah. Oh, this one. Right.
Okay. All right, so you just tell me when to.
So now I have to tell you when to click.
Yep.
All right, click.
Oh, you can give him.
Sounds good. Okay, so here's what I was talking about, right? What we can do is we can rigorously define this measure as the product of measures of the fields at each point in space. Thank you, Sonia. I'm sorry. You'll have to now listen to my talk. And so we can do this for different points in space, right? And so generally what we can do is just define our four-dimensional lattice, right? Where we have three-dimensional space as well as time, discretize each one of these puppies, put some spatial extent, and also we have to generally truncate our space-time. So we can't do even infinitely large discretized space-time because we only have a finite amount of computer memory, and so we can only store information regarding a finite discretized space. The spatial extent is L. Generally, we do calculations in cubic, periodic boundary conditions, which I'll talk a lot more about that tomorrow. And then there's some, temporal extent, which, is our fourth dimension. There's also this requires us to introduce an intrinsic violet cutoff, which is a lattice spacing. This is the smallest separation between all points in space. These don't have to be the same for each direction. Generally, they are. Some of us are crazy enough to do anisotropic calculations where the spatial part may be less or more fine than the temporal part, but that's a technicality, okay? But once we've done this, for each point in space, we can define the integral of the field. This is still impractical. And so what we do in practice is instead of aiming to solve this whole integral, we are gonna do statistical estimations of this integral. And so to do this, what we can then do is instead of evaluating the Minkowski path integral, which is a thing that we all, are more familiar with, we evaluate the Euclidean analog of this. And so you can just do it by Wick rotation. After a little bit of algebra, you can show that the I to the action becomes negative S of the Euclidean action. And so you have something now that is positive definite. And so this is something that if we can't solve analytically, we can hope to solve it statistically by just sampling over the distribution of fields that satisfy, not that minimize the action, but that have the same distribution as e to the minus the action. And instead of going to all the details here, I just have a little bit of proof of how just doing this Wick rotation where we grab time and make it imaginary with a factor of negative I just leads this to this. And so I have a proof. I'm not going to bother to walk through it because it's just tedium. It's just algebra. Okay. So here it is. And so once you have this, what you can then do is generate a set of field configurations that have the probability distribution weighted by this. And so these are called field configurations. So there's just some finite number of field configurations, depending on the lattice, depending on the space time, the size of your volume. You may have to go to something in the order of 100 or thousands, in some low dimensional field theories, you can go to like millions. But you're limited then by the amount of computer time that you have and computational storage. But the point is that in doing this, we don't have to make any assumptions about the dynamics. And so it allows us to study any field theory. I haven't talked about QCD yet, but any field theory in a way that is non-perturbatively at the cost of solving the theory or studying the theory statistically, right? We've made a bunch of truncations into the theory. We butchered it, right? We introduced a finite infrared cutoff, which is our finite volume and space-time volume, also an ultraviolet one. Also, we've wick rotated. All these things should give you pause, and we'll talk about all these issues, okay? But nevertheless, I can study this Euclidean finite discretized lattice statistically as opposed to making dynamical approximations. So it's very different. Here's a little workflow on how you can, imagine Monte Carlo sampling taking place for some field theory. But the point, I don't really want to go into these details. So then, once you've generated a set of field configuration, what we know from quantum field theory is that any observable that I'm after, I can write it as an expectation value of some operator sandwiched between the vacuum. Almost anything, any function I can either write it the observable this way, or I can deduce it from an observable that can be written in this form, or at least a large set of observables. And so this in quantum field theory, this operator language, I can always write it in the path integral language by just saying I'm going to integrate over my path integral with some field definition for these operators. And so using this representation, I know that I can now describe this object in the left, this expectation value of matrix, as the average of it. I can obtain it by averaging over my field configurations, where I now evaluate this object under the n samples of my field. And so I can average over these. I can also construct the statistical uncertainty associated with that. And then at the end of the day, I can quote an estimation of a given observable with some, with its mean value and a statistical uncertainty for that given lattice, for that given volume, lattice spacing, etc. So this is the key idea. Maybe before I jump into QCD itself, are there any questions about this conceptually, at least? Straightforward, or too fast to, I've gone too fast to even know what to ask? Hopefully it's not the latter. I'm not so mean, so you can ask whatever questions you want. Okay, so QCD is of course not a scalar field theory. So how do we introduce quark fields and gauge fields? First, we need to make sure that our discretized action is gauge invariant. And so the way that you can do this is so if we introduce, what we want to do is basically discretize our derivatives in the action. And so this requires us to evaluate fields at different points. We want to make sure that this doesn't break gauge symmetry. And so the answer to solving this is introducing Wilson lines, or in the lattice language is to introduce gauge lines. And so we know from continuum field theory that if I have the fields evaluated to different points, here I'm talking about my fermion fields, the product of these two guys won't be gauge invariant, but I can always introduce a Wilson line that connects these two to make it gauge invariant. And so that's exactly what you can then do, and if you have a lattice version of this, and I have 2 points in space where I'm evaluating my fermionic fields, I can construct little Wilson lines, which are products of Wilson links, which is just a minimal size Wilson line in our lattice, which is just basically pointing from one point in space to the nearest neighbor. Okay. And so this object, it lives in the is an object over the SU3 algebra, and it's just that this is really the object that appears in the Wilson action. And so then what we can do is define. There's a lot of freedoms in how you define a discretized version of the QCD action. Basically, all of these, there's many different versions of this. There's pros and cons to various different ones, but the important thing is that in the continuum limit, they all have to agree. Okay? And so if I have points in space that are separated, so in the so basically this is one version of the fermionic part of the Wilson action, where now the points are separated by the Wilson by these gauge lengths, and by taking the continuum limit, a goes to 0 analytically, you can show that indeed this object reduces to the fermionic part of the QCD action. So here's a perfectly fine object. We can construct many other ones. Different ones have better advantages of how they quickly approach the continuum limit. There's a choice, a technicality, and there's ones preserve some symmetries better than others. And so there's a whole market out there for different for different actions on the lattice. And at the end of the day, I can write this object in the lattice as a matrix, that lives in my space-time, as well as my other degrees of freedoms like color, spin, and it couples fermionic fields with antifermionic. And so having that, then the challenge with now having both. So if we want to now simulate actual QCD with fermions and gauge fields, what I have to evaluate is the path integral associated with this. You might imagine that we would have to then worry about the fact that the fermions are anti-commuting fields, and they're described by Grassmann variables. But the beauty is that the action is bilinear in these variables, and so we actually can integrate this analytically. And so then you're left with a determinant. This determinant depends on the gauge fields, right? Because the quarks are coupled to the gauge fields. And so actually the gauge part of the action is the hard part to evaluate. Because then you have to, this is the part that we don't know how to solve analytically. And instead, this is the part that we actually Monte Carlo sample. And so this gives you a sample of gauge fields that you then have at your disposal. And then you can write every single observable as, in terms of building blocks that are described by the inputs being those gauge field configurations. So one of the many objects that is critical in a lattice calculation are the quark propagators, which is just basically the correlations between quarks at one point and at some other point, with all this, with all the color and spin indices being shown explicitly. And this is just basically just walking you through the algebra, how you go from from this expectation value to the path integral representation, all the way to basically evaluating the inverse of the Dirac matrix is what ended up here. And this is basically the building block to many correlation functions, which I'll be discussing in a second. How am I doing in time? I guess I got like 20 more minutes. Fantastic. And so, for example, the simplest correlation functions that we can imagine evaluating are called two-point correlation functions, where I have some single particle state. Let's say, let me correct that word. What we claim to do with lattice is this will never give us access exactly to a given state. So we will never, at this point, claim to ever resolve an actual wave function or an actual state. What we can do is determine slices of a given state. So we can claim to obtain information about the mass or perhaps matrix elements of that given state. And I'll tell you how you do this. And so what we use instead are interpolating operators that we know have the right quantum numbers to those states, but they're not actually the things that will exactly create those states. What we can evaluate are correlation functions with something that has the quantum numbers of a given state. So imagine that I wanted to calculate the correlation functions of pions. This is how you would do it. So, or this is one way to do it. You would construct some operator that has the quantum numbers of a pion at rest. And so it would have to be a pseudo scalar. So I put a gamma 5 in there. And so that at least takes care of parity. Then in spin. Then if I wanted to, of course, have more careful treatment of the flavor content, right? Then I have to tell you which psi I'm picking for each one, right? So there would be some choice there. So if I want to do the pi plus versus the pi 0, then I have to be careful about which fields I'm using there. Then I also, in this case, I'm interested in evaluating, let's say the pion at rest to have zero momentum. And so what I want is an operator that has some definite momentum, and it would be, in this case, zero. So how do I do that? I just grab the operator that is at space, and I integrate over all possible points in space with no weight, and that will give me the pion with no momentum. And so that's what I'm doing here. And I described that in some details over there. And so this will give me the correlation function that has the quantum numbers associated with creating a pion with zero momentum and annihilating a pion at a later point with zero momentum. Okay, and so that's what I'm doing. And then here I'm actually doing a little bit of a trick, which is that I just put this operator at the origin in space, which is a choice. I could have done something different. There's many choices here. So the point is that if I grab this object, I can use Wick contractions, and I can evaluate the correlation function as a sum over all possible Wick contractions. After a little bit of algebra, and I'll leave this for homework, you can show that this thing, it can just be written as a trace over my propagators and gamma matrices. And then that's it. And that's actually what we evaluate on the lattice. It's actually, in this case, we will evaluate this trace in your computer because you have these propagators laying around. They're large matrices. You can insert gamma 5s and take some large trace. And that's a, the bread and butter correlation function that you want. And you will calculate this for different points in time, and that will give you information about the spectrum, as I will show in just a second. Okay, and diagrammatically we can represent this as some source with gamma 5, some evolution at later time, and some sync with gamma 5. And here I chose one particular type of source that is very common, which is point to all propagators. So these are things that have information coupling one point to all points in space. But I could have done something else. There's many choices. Okay, so that's kind of the generality of lattice QCD. And so let's zoom out a little bit and say, what is this bias, and how do we actually start doing calculations? I mean, the beauty of QCD is that it's a fundamental theory. It's fixed by a finite number of parameters, which are just the quark masses and then some coupling, some unknown coupling. Via this fancy word of dimensional transmutation, which is like in a given field theory, you start with something that is dimensionless, and then by doing renormalization, a dimensional quantity appears, which is lambda QCD. The whole theory can be described by ratios of dimensionless quantities, right? Quark masses and some unknown parameter lambda QCD. Experimentally, QCD itself doesn't have any mass scale. There's nothing in the theory that tells you like, lambda QCD has to be blank, right? Instead, you fix it experimentally to some, doing some analysis, and you get some value, something in the order of like 200 MeV, right? And this then now starts to introduce scales into the theory. In lattice QCD, the parameter that appears is you have the quark masses, but then is the lattice spacing. That's the parameter that appears. Lambda QCD itself doesn't appear, but you still have some dimensional quantity, which is in a length scale, which is the lattice spacing. And the key point is that you can imagine by fixing all these parameters using various different low-lying states, you can then tune all the quark masses, and then you still have some scale that remains. And so again, QCD, what will honest to God give you is ratio of dimensional quantities. So I can always calculate the ratio of, say, the proton mass to the lambda baryon mass and things like that. We can quote those very well. But if we then want to compare with experiments, I have to give up some quantity. And typically the lattice spacing is replaced with some other quantity. One choice would be, for example, fixing the lattice mass of so what you calculate on the lattice. And I haven't told you yet how we would do this, but let's say the omega baryon, you'd say, I calculated this on the lattice, and then I would fix this to the lattice spacing, which I don't know what it is, multiplied times the experimental value of the omega baryon. And so then this gives me a definition of the lattice spacing as A omega lattice over A omega experiment. And of course, this would just be some number that we calculate on the lattice. And so then this would give me definition of the lattice spacing now for my ensemble forever. Okay. And so, but after that, we're in business. Everything else is a prediction, right? Once we've tuned these parameters, because QCD, you know, we've been treating QCD exactly, I can predict everything else that is under the sun. And so generally, here's the workflow of lattice calculations, right? You pick your action, you discretize your action some way, you tune your parameters to that action, you generate some field configurations. This is serious computing. This takes a lot of work to be able to do this, and a good chunk of the computational power goes into that. Then you calculate your quark propagators. This is, you know, again, serious computing, but you calculate them once and then you store them, and that's it. They're the same quarks that, you know, quark propagators that you would use for studying, you know, the pion form factors or the proton GPDs or whatever, right? It's the same thing forever and ever. But so you calculate these things once, store them, and then after that, it's a matter of evaluating correlation functions for your one observable that you want to study in some detail. And then there's a bunch of analysis that needs to be done, and eventually, hopefully, you get to some interesting physics. That's roughly the workflow of lattice calculation. So, okay, I guess I can give myself a check mark for as to why lattice works, right? It's just a different way of thinking about lattice QCD or thinking about QCD, but it gives us a method for studying the theory without jeopardizing the dynamics and just introducing statistical uncertainties that we can always improve by beating down the uncertainties, right? Just generating more and more field configurations and doing more sampling. That's the beauty of it. So are there any questions before I move on to the next? Yeah.
Just a question about when you said you use interpolating operators. I wonder how many do you, like in principle, you have different operators with the same numbers, I guess.
There's an infinite number of them.
Right, so how do you decide which ones and how many?
The limitation, I mean, the answer to both of those in practice is what can you do? Because even though the computational cost of correlation functions is a small compared to the rest, it still could be quite costly. And so in general, what you can do, and this is, I was gonna talk about this tomorrow. So in general, let's say that I have, let's think about just the pion, right? So the pion, you know, there's an infinite number of states that have the same quantum numbers as the pions. And if we think about, even without thinking about the quark content, because we don't know what the quark content, I mean, we know what the minimal quark content is for the pions, right? There's QQ bar, gamma 5, Q at the same point, right? But I can displace these guys with gauge lengths, right? So I can introduce like U in such a way, right? Depending on how I introduce this, I can start introducing non-zero angular momentum, right? So I need to make sure that this is being projected to zero angular momentum, right? But once I start imagining this, right? You know, there's really an infinite number of gauge length configurations that I can imagine. So just in the quark model, if we quark model like construction of pions, there's an infinite number. And we take advantage of this. So we construct many operators that have basically different, you know, that are identical, that have the same quantum numbers, but they're different configurations of quarks and antiquarks. But then you can also imagine that, you know, a pion on its own has the same quantum numbers as 3 pions. In fact, you know, if I make sure that I project this to say, you know, the 0++ JBC, right? And so, in fact, this has the same quantum numbers as like, you know, any n product of these guys. So there's really an infinite number of these guys. There is a little bit of intuition that has been built that, you know, there is a mass gap between these. And for some reason, quark model operators do seem to do a good job of getting you ground states. And so starting to construct more complicated multi-particle operators resolving ground states is a bit of an overkill. But it can be relevant in extracting matrix elements because the excited state contamination comes from these guys. And I'll talk about that a little. Yeah. Yeah, what's up?
You mentioned that the Wilson line ensures engagement variance, and I know there have been recent calculations, might not need the Wilson line, but has there ever been tests using a different type of engagement variance between the two, if there exists?
I mean, so introducing a theory, so doing calculations without that are, or with observables that are gauge invariant can in principle be done. There are systematic errors associated with that that one has to be cautious about, but in principle, it can be done. People have done various different calculations. But what the question was, have people done tests of doing, either like having a gauge invariant calculation of some observable without another one with a gauge without imposing gauge invariance? Is that was the question?
My question was, have they replaced the Wilson line with some other link that ensures gauge invariance?
Yeah, I mean, in a sense, for the different actions that are introduced, that are basically that have been used to improve on discretization effects, basically amounts to having more complicated versions of like Wilson lines and plaquettes built into the action. So it's not like you don't have to have the simple nearby nearest neighbor Wilson. So in a sense, yeah, I think that's what. Yeah. Any other? Yeah.
Sorry, probably I missed. Any specific reason to use the omega to determine the?
It's just a choice. No, it's just, I'm just saying, I'm just giving you one choice. Yeah, there's different scale settings out there, like, there's basically almost one scale setting per collaboration. At the end of the day, everything has to agree in the continuum and physical point. So it's just, you have a freedom and how you tune your parameters and set your scale. But ultimately, at the end of the day, everything has to agree in the limit that basically you extrapolate to physical quark masses, or you do your calculations of the physical quark masses, and you take the continuum. Anything else? Yeah.
Sorry, it's a basic question. So if you want to probe these non-perturbative regimes in which you're gonna have a lot of paths which contribute other than just the classical one, how do you know if your sample is like incorporating enough?
So I mean, typically what you test is convergence of a simple observable as a function of the trajectory of the number of the field configurations. So you basically do this workflow that I was describing, that I kind of basically jumped over, which is you generate some field configuration. You test the likelihood of that being accepted using e to the minus s as a probability of whether you keep or reject that gauge configuration, and then you generate a new one. The way you generate the new one, there's different methods out there, but basically hybrid Monte Carlo is the main way of doing this. So you start generating a bunch of different configurations that you then keep, and then you evaluate some observable as a function of the trajectories. And so, like, you start sampling your, some here is like your number of fields, okay? And so you might start with like a hot or cold configuration. Imagine that I had just like something like the icing model where I start with like everything pointing one direction or everything completely random, right? There's going to be some bias to some observable there, and it's going to be, some value on it, right? And I'm going to be sampling different configurations, and then at some point, I will start having a healthy distribution of fields that is being sampled around what seems to be the average, the statistical average of that observable. Then what I do is that I keep some number of these guys. I don't keep everything. So there's going to be strong correlations from one point to another. And so you keep some number of these guys, or you do binning over these guys. So I can do, some binning of this, so average over these fields over here, and that would be my new field N1. There's really some number associated with the field. And then I do the same over here. But it's basically by looking at observables and making sure that they're statistically fluctuating about some mean, that you deduce that basically that there's been some convergence at that point. And then after that is a matter of making sure that you're not just sampling one point, but you have some ensemble that is being distributed by this probability distribution. Does that answer your question?
Yeah.
Okay, cool. Anything else? Okay, okay, I got 5 minutes. Ooh. All right, so,
We have some leeway, so. take your
okay,
time.
sounds good. Okay, cool. So one thing that I think it's not really emphasized enough, but lattice QCD is kind of like a perfect theory for lattice methods. And maybe I wrote this in the, no, okay, here. The beauty of QCD is that it's perturbative in the large regime, right? So we've introduced some cutoff, essentially, or an ultraviolet cutoff. And the nice thing is that because the theory is perturbative in the large regime, this means two things. One, that if there's some errors associated with this, I can in principle use perturbation theory to correct for these errors. Or if I have renormalization dependent quantities, I can also use perturbation theory for me to connect the observables that are calculated with this ultraviolet cutoff with the quantities in your preferred renormalization scheme. And so that allows us to do matching to, things that have been calculated in MS bar and some renormalization scheme and some renormalization scale. But it is also the case that if you have renormalization independent quantities like the spectrum, they will still suffer from discretization effects, right? So there's going to be some error associated with any one observable. Here I'm saying X, but this could be a mass that, it's going to be equal to the mass in the continuum limit up to discretization effects if the action is sufficiently fine that, these effects are indeed in the perturbative region, right? If the scale is too small, then, maybe these effects are going to be large. But if I'm in the region where the lattice spacing is sufficiently small, then there's going to be linear order terms that maybe you can extrapolate away, or you can improve your action. This error is not linear but rather quadratic, and you can be in business, right? So lattice QCD is a perfect, or QCD is kind of a perfect theory to study using lattice QCD because of this one issue. So now let's talk about time evolution, because most of the observables that we study are via studying the time evolution of correlation functions in Euclidean space, which maybe sounds counterintuitive because this seems like something that we essentially butchered the theory by putting it in Euclidean space-time, but it's actually a winning point. So we've mentioned already the evaluation of 2-point correlation functions, where I have something I create at some point in the origin, and then annihilated some later time in time in Euclid, or in time. And here omega is the vacuum. And so in Minkowski space, we know that this time evolution operator evolves like this, where I have the field evaluated at the origin, and then I have the time evolution operator on the left, and then the conjugate on the right, or the other way around. By Wick rotating, this is no longer an oscillatory behavior, but rather an exponentially damping or exponentially growing behavior. If I then write this in Euclidean space, the correlation functions that I want are these, okay? This is what we actually evaluate. And then after a little bit of algebra, what I want to do is insert a complete set of states. And so here I've inserted the identity by saying, the identity I can always write as sum over n over this outer products of my eigenstates of the Hamiltonian n. And so I insert it over here. And so then the H acting on n will give me an energy. H acting on the left hand side will give me a vacuum. If the vacuum has 0 energy, then I can ignore this. Otherwise, I'm evaluating energy differences. And so from the time dependence of these correlation functions, you can imagine teasing out spectra. That's great. There is one subtlety, right? Here I use a complete set of states, and I assume these guys are discrete, and nobody yelled at me. And so this is something that we should worry about, because in the infinitely large space-time that we live in, we really have a continuum of states, right? We can shoot particles at any continuous momenta, right? And so is this really a sum or should we be integrating? And here's where our infrared cutoff comes to save us. So we've introduced a finite spacetime, which means that by definition, so we need to impose some boundary conditions. Typically, we impose periodic boundary conditions. And this assures that the spectrum is discrete, right? There's only some discrete set of modes that are periodic in our given lattice. And so that means that the spectrum here, I'm showing the spectrum in the complex Mandelstam variable S, is discrete and purely real. This is very, very different than an experiment. So this should also give you pause. And this is what I'll talk about more tomorrow. So this is very, very different. This doesn't make sense if we want to compare it to experiments, but the nice thing is that this is a sum, okay? So how do we connect it to experiments? In general, it's not trivial, but it at least is a sum. So that part we can convince ourselves. And so maybe the last thing I'll show is that using the spectral decomposition of correlation functions, then I can write this as a sum of states at large enough times. This will be saturated by the ground state. There'll be some corrections associated with the next decided state. Because in QCD there is a mass gap, that's the other thing. QCD not only is perturbative in the large energy region, but it also has a mass gap. So there's always a gap between a bound state and the next open threshold. So there's always some energy gap here. That assures that there's always going to be some state that dominates at large enough times. And so this introduces the motivation for what is called an effective mass, which is basically just grabbing ratios of correlation functions. And after a little bit of algebra, this object you can show at large enough times, it should plateau to, basically a ratio of the logarithm of ratios to exponentials, which, just ends up being the single energy. And so this basically is what correlation functions generally look like. They're just sums of our exponentials at large enough time. They start to decay. If we plot the effective mass for this guy at sufficiently large times, it will plateau to some given value. And this is just a toy model of an energy. Real lattice data looks like this, where if you grab the correlation function and you multiply times, instead of constructing an effective mass, you multiply times e to the energy times time. As a function of time, this will plateau to 1. It should plateau to 1, and there will be some energy. There will be some error distribution associated with this data because you statistically sample this. And so at large enough time, you can just do a fit and obtain some energy level associated with that. And maybe the very, very last thing I will say, and then I'll shut up because I'm over time, is that the thing that assures that you can faithfully obtain properties of stable particles, and then tomorrow I'll talk about resonances, is the fact that QCD is a short range force. And so that means that if I put particles in a box of any kind, let's imagine a periodic box, the errors associated with putting the particles in a box are going to be because they interact with the boundary conditions. They interact with, in this case, with their images, because the theory is because I put periodic boundary conditions. If you think about the difference between the particle and its mirror image, that's going to be a length L, which is the size of my box. And because at large distances, I can describe the interactions of, say, 2 protons being described by the Yukawa interaction, which decays exponentially because the theory is in short range, right? The Yukawa potential goes like e to the minus m pi r, but that doesn't really matter. You can imagine that the error that I'm making from obtaining the spectrum of this proton, the mass of this proton in a given box, it scales exponentially with the distance associated with this box, and the scale that appears is always a pi m mass because that's the tail of the low energy representation of the QC potential. So for sufficiently large boxes, and the thing that sets the scale in every single lattice calculation is the lightest mass of the theory, which is the pion. So for sufficiently large, what we mean is large compared to the only low energy infrared scale, which is the pion, the inverse of the pion mass. Then we are sure to have exponentially small errors for any observable associated with single particles. And so you can prove this also in field theory, and if you want to see a proof, talk to me about it in the discussion session. But this at least gives you like more warm and fuzzy that like this works okay, you know, as long as we have volumes that are sufficiently large for single particle states. And you can see this behavior. So there's the spectrum of a pion for 400 MeV pion mass roughly, and you can see the exponential behavior as a function of the volume. So I should really stop here. But the idea is that this works, this is, you know, basically you have all these different scales, and the beauty, I mean, basically QCD is kind of perfect for lattice calculation. It's perturbative in the UV region. There is a mass gap, and it's a short range force, and so you can shove it into a little box. And here the boxes are tiny, you know, we're talking about like the order of like a few Fermi, so we can get away with murder. We can do Wick rotation, do things in Euclidean spacetime, and get observables that are at least insensitive of time. And I'll talk about more observables later, so I should really stop. So, any questions? Yeah, what's up?
So here this mass should be Vela's mass.
There's no, so here the theory is unitary, which means that the action that was used in generating the quark propagators, so the action that was generated for generating the fields and the quark propagators is the same. So the C and the valence quark masses are the same, which means that there's only one pion. Yeah, you can break unitarity if you want. Yeah.
They are different, so which one should be used as this finite volume?
Yeah, so once you start breaking unitarity by using different actions for generating your fields and the quark propagators, things get much more complicated. And basically, the answer is don't do it if you can. You know, this is something that has been done historically because of limited resources, but there is effective field theory arguments that basically suggest that this is something that is not a damaging issue for observables associated with single particles. Basically, because there's nothing that really goes on shell, these errors come at the discretization of they can be hidden into discretization effects, and so you still get this kind of behavior. It's just you then may have large discretization effects that you have to remove by taking the continuum limit. So the overall scale, you still have some scale there. Which is it in terms of like whether it's like the valence or the C pion, depending on like I don't know, actually, is the honest gut answer. But it would be some scale, which you can always fit away. You can say, I'm going to do my calculations in multiple volumes and lattice spacing, so I'm going to be agnostic in terms of what that scale is and just fit that parameter. That's probably the best thing to do. Yeah. Interesting question. Yeah.
Does the finite volume effect depend on the source we use to generate the particle? For example, if we use wall source to project this hadron state, is the finite volume enhanced compared to the point source?
That's a very good question. So I think no, the answer is no. So if you, I mean, what will happen is that these contaminations associated with, okay, so some of you clearly are experts on that stuff. So the correlation functions, right, are sum over exponentials, right? At large time, it behaves like this. In general, it doesn't, right? And large time can be very, very large. And so this is like a simple way to think about this, but it's not the best way to extract spectra, okay? But nevertheless, you can, basically, if you do this, you will always have contaminations from states that you're not taking into account in your analysis. This is what people refer to as excited state contamination, because they're energies that are excited. And so what will happen is that the spectrum will be the same, independent of the operator that you use. But the coefficients in front, these coefficients are very dependent on the operator. So here I've assumed that my operator at the source and sink are the same, right? But in general, they're not. And so you may have better or worse overlap with a given state. And in fact, you may, introduce maybe this scaling, this exponential decay scaling is compensated by your operator being one that really wants to latch on to some excited state as opposed to the ground state. And so depending on the operator, you may have a harder or an easier time resolving a given state. Yeah. So you definitely want to do calculations where you introduce, so the way you can circumvent these days is by constructing a large list of operators and doing an analysis that is agnostic to your one operator that you have, an emotional attachment to. Does that make sense?
I mean the finite volume effect.
No, so the finite volume effects come from the spectrum. The spectrum is independent. So this exponential behavior is independent of how you access the spectrum. Yeah, so think that there's some spectrum of that given theory, and you're trying to do whatever you want, whatever you can to extract that spectrum. You use some operator, I use some operator. We all have to agree on the energy of that state. That state will have this kind of behavior if it's a single particle state, and that's independent of how we extracted that state.
Yeah, so when extracting the ground state energy, it's been seen that the higher you boost in momentum, the more noisier the data gets. I guess where does the error come from in the boost of momentum? And at what point in these calculations?
So you can do, where does it come? So you can argue, so you can use a Lapage kind of argument for this, and I can maybe walk you through that in the discussion session. The noise, the way you can think about it is that you're doing an averaging over your space with a so you've introduced a phase, right? And so that's part of the source, is that you're doing an averaging over space with some phase, and you don't have so for any one field, you don't have translation invariance. And so momentum is not a definite quantum number. Momentum is something that is recovered statistically by sampling more and more fields, and that basically leads to translation invariance being recovered. And so you're sampling over a phase, you're introducing a phase over a theory that you've partially broken spatial invariance. And so the low energy modes are going to be better estimated in a theory where you've basically lost translation invariance, because you can imagine that basically the translation invariance distortion is a UV one. And so that's part of the source of where this phase comes in. But also you can also argue this using Lapage arguments, saying that the variance of a correlation function is itself a correlation function. And so you can estimate what that variance is. And it's going to be, depending on the state, you can always argue there's going to be the variance will decay less fast with time than the correlation signal. That will take me like 5 minutes to walk you through it. We can do that later. Yeah. All right. Anything else? So let me see. Yeah, so we'll pick up this tomorrow here. We'll talk about the limitations. I'll show you some more plots, and then we'll talk about scattering observables. And yeah, be happy to talk to you guys later. So that's it. That's all I got. Thank you.
And again, we'll have a discussion this evening at 7:30, so you can save up your questions and put those together then. We'll take a break. Let's break for half an hour. We'll start at 1:15. And again, it's a tutorial. I'm not going to lecture. We're going to use Python in the Jupyter Notebook. We can do it in the virtual box or out of the virtual box. We're also optional, but we're going to do some math. If you want this Mathematica and real quick, a TMD plotter. If you have any glitches on the computer, I'll take those during the coffee break. So at quarter of, we'll just jump right into it. And basically, I'm going to, the homework, the problem is you're supposed to make some plots, and that's what we're up to. So have a good coffee break. We'll see you in half an hour.
Thanks for
Oh,
sacrificing your slides.
Oh,
or your-
Well,
I don't know.
yeah, it's just as a behavior.
I don't know why, like, I've had this problem happen many times when I print out a PDF. I think it's Keynote